Welcome, everyone. Thank you so much for joining us for OA Week 2023. My name is Sarah Flickinger, and I'm an Associate Research Scientist at the OAICC, and I'm also a member of the GOA-ON Secretariat. Before we get started, I'd just like to note that this session is being recorded and will be posted on YouTube at a later date. So just to start, OA Week is presented by 4 sponsoring organizations. First, GOA-ON, the Global Ocean Acidification Observing Network. Second, NOAA, the United States National Oceanic and Atmospheric Administration. Third, the IAEA OAICC, the International Atomic Energy Agency Ocean Acidification International Coordination Center. And finally, the IOC, UNESCO, the Intergovernmental Oceanographic Commission of the United Nations Educational, Scientific, and Cultural Organization. GOA-ON was started in 2012 with just a handful of members, and now in 2023 we have grown to over 1,000 members from 114 countries with quite the global span, as you can see in this map here. We also are represented by 9 regional hubs, which span across the continents and oceanographic regions, represented by the logos in this plot, and we'll be hearing from most of them throughout OA Week this week. If you are not yet a member of GOA-ON, we welcome everybody, and we would love it if you could join GOA-ON by visiting goaon.org. OA Week debuted in 2020 and returned in 2021 when events and conferences were postponed due to COVID-19. Following the successful in-person symposium on the ocean in a high CO2 world in 2022, GOA-ON is bringing back OA Week 2023 to maintain momentum around OA research and provide a virtual platform for the ocean acidification community to exchange their latest findings. We are thrilled to present a wide range of ocean acidification topics and speakers from around the world. So before we dive into our speaker presentations, a few quick logistics that I'd like to go over. During today's presentation, all participants will be in listen-only mode, and we welcome any questions that you have for our speakers in the questions box, which is located at the bottom of your screen in the toolbar labeled Q&A. We'll be monitoring these incoming questions, and our moderator will pose them to the speakers during the question and answer section immediately following all of our speakers' presentations. And during this discussion at the end, you can also use the raise hand function, which you can see again in the bottom toolbox at the bottom of your screen. We can call on you to unmute and ask your question directly. So without further ado, I would like to introduce our moderator for this session. Dr. Kaitlyn Lowder supports EQUISEA at the Ocean Foundation and works to increase ocean science research capacity around the globe. In her capacity as a program manager, she leads international training workshops for scientists, delivers low-cost sets of equipment to initialize monitoring programs, and develops resource materials to enable high-quality methodology that is accessible to lesser resourced research groups. Kaitlyn, so thank you so much for organizing the session and for being here today, and the floor is yours.
Thank you, Sarah. I'm really glad to be leading the session. So as the ocean acidification community has continued to advance the tools and techniques to effectively conduct OA research globally, we'll hear about some of those range of approaches to improve the ability to measure carbonate chemistry, including through capacity building and writing practical research guides. We'll hear about identifying impurities of meta-Cresol purple to improve quantification, and finally, the work to develop a calculator for quantifying pH measurement uncertainty. So we have 4 speakers today. We'll go through each of the presentations and hopefully have about 10 minutes at the end for Q&A. So first off, I would like to introduce our first speaker, Dr. Andrew Dickson. Andrew is an emeritus professor of marine chemistry at the Scripps Institution of Oceanography of the University of California, San Diego. His research interests include oceanification, quality control of oceanic carbon dioxide measurements, biogeochemistry of the upper ocean, marine inorganic chemistry, thermodynamics of electrolyte solutions at high temperatures and pressures, and analytical chemistry of carbon dioxide in seawater. Andrew previously served on the NRC Committee on Oceanic Carbon and was the chair of the NRC Committee on Reference Materials for Ocean Science. His laboratory at Scripps prepares, certifies, and distributes reference materials for ocean CO2 measurements to laboratories all over the world. So welcome, Andrew. We'll turn the floor over to you.
Thank you. So today I indicated that I would talk about capacity development, particularly with a focus on seawater CO2 measurements. And I gave teasers for other parts which are perhaps less included. One is what's really required, and I will talk about that. But the other, which is a little harder, which is, can it be implemented effectively? How can you do that? So here basically is a follow-up to the history from before, earliest meetings being over 10 years ago, and growing from the OceanObs discussions of about 15 years ago to say, what do we really need to study ocean acidification effectively? And it became recognized that there were two substantially different parts. One, the very first world research aspects that many in countries like Europe and the US were focused on. But second, for ocean acidification, in that this affected everybody, there was an important need to get as many others all around the world involved in understanding how this was affecting their local resources and how they could monitor it and think about it as a local problem. And that's really the introduction to capacity building that we're talking about here. So initially, my thanks to three main groups: my NOAA colleagues and GOA-ON for inviting me to participate in this meeting and in a variety of other GOA-ON meetings over the years; the IAEA Ocean Acidification International Coordination Center, who invited me to participate in a variety of training courses over the last decade or so in what were, for me at least, usually exotic locales. Although I thought I'd traveled a lot, this gave me an opportunity to visit a number of places I had never been to before. And finally, the Ocean Foundation, who distribute a GOA-ON in a box kit, along with accompanying instructional videos available on their website, or linked to YouTube from their website. And these three really are the parts that build my knowledge, that is what I'm talking about here. So what really is capacity development? Well, the real key is that you're trying to get people, organizations, society able to manage their affairs successfully. This is not just a simple show and tell, the technical assistance, which really just aims for expertise and training, but really saying, how do we help you to do it for yourself? The goal really is that you're trying to build a sustainable capacity in some regional community, encouraging both local training and, where practical, use of local equipment, while still remaining responsive to any regional needs and perhaps coordinating with other donors and partners. Typically, this has often been seen as the key feature, the technical assistance, the training courses, here's some equipment you can use, etc. But really, we want to get groups all around the world thinking about this as a problem that they themselves are well equipped to deal with. So with the CO2 system, there's always been this emphasis on high quality measurements. And my own laboratory is no exception to this, where the real goal has been to ask how the oceans are changing, which requires very, very careful measurements in a lot of places, ideally done as quickly and cheaply as possible. But that's not the only reason we need to measure seawater CO2 in the context of ocean acidification. There's also the need to better understand how the changes in ocean chemistry affect the ecology and life in the oceans. So this makes me think, well, how would you define what is quality? And thinking what you need, you have to have this in mind. You need to know that it actually does what you want. It's suitable for the purpose you intend. Where the purpose you intend really means that the data you're producing can be used by a user to make a particular decision for a particular purpose. Notice there is nothing here that says this has to be the best data in the world, the most precise data in the world, the fanciest measurement technology in the world. All it says is that the data is needed so it can be useful. And ultimately, this is referring really to how uncertain a measurement is relative to what you need for a particular application. And so, in what I'm focusing on here, I'm looking at what are perhaps not state-of-the-art measurements, but somewhat simpler and more straightforward ones. This has implications for the resources you need, both the human resources, the people that are actually doing the technical work, who would need significant training to do it at all, and extra training if they're going to do it with expensive and easily breakable equipment. And you need different equipment for different achievements. So what do we really need for ocean acidification? There's been two versions that I found looking around. One comes from the California Current Acidification Network, who wrote that measurements are required that enable the saturation state of seawater with respect to aragonite to be determined with an uncertainty of plus or minus 0.2, and that also enable a complete description of the seawater CO2 system, including pH and PCO2. We'll come back to that last line in a few moments more. This is to be compared with one from the GOA-ON document, which basically says the weather objective requires the carbonate ion concentration used to calculate saturation state to have a relative standard uncertainty of 10%. These are similar magnitudes in what they're looking for, but it's defined in terms of the saturation state of aragonite, not in terms of what you would normally actually measure, because the saturation state of aragonite or carbonate ion concentration is largely a calculated parameter, calculated from other measurements. So what's commonly measured? Well, coastal pH is easy to measure. Well, relatively easy to measure because automated equipment exists for it. These are all US examples, but you can see a variety of measurements made by different groups in different locations that show various trends. And if you look at the scales, you can see the differing degrees of sensitivity depending upon the equipment being used. In particular, on the right-hand top, you can see diurnal cycles. You can see those two in this mooring data. So you can get a lot of pH data relatively straightforwardly if you have the right instrument and if you can keep it rated and maintained. But pH alone is not enough. An unambiguous description requires significantly more information. You need to know the relevant equilibrium constants. These are in the published literature. But for any individual sample, you need at least 2 carbonate system parameters to be measured. The usual 4 are the pH, the partial pressure, PCO2, total carbon, and total alkalinity. If alkalinity is one of the 2 that you actually measure, you need some additional information about any non-CO2 acid-base systems, such as borate. You need the total concentration, and you also need any relevant equilibrium constants. You can't identify a single CO2 system parameter as being responsible for biological responses to ocean acidification. Is it pH? Maybe for some things. Is it PCO2 for others? Saturation state? Perhaps for others. You also end up, because of this needing 2 measurements, you can't design experiments that just allow you to change one thing. You can't say, I'll keep everything the same and change the pH. That cannot be done in a seawater system. And of course, to recognize that although we talk about ocean acidification as this large process with us burning fossil fuels, putting CO2 into the atmosphere, CO2 ending up in the ocean, actually, if you're an organism living in seawater, you don't care how it got that way. What you really are adapting to is the actual composition of your surrounding seawater, which varies with time, but largely that's due to changes that come from biological activity. On a slower scale, there may be other mixing changes and gas exchange with the atmosphere, the gradually increasing levels of CO2. So as I said, a common approach has been to use this aragonite saturation state as an OA proxy, in part because of the pictures like at the top left, where you can see that between 1880 and about 2012, this was a very early picture in the GOA-ON thinking, there's a clear change in aragonite saturation state at the ocean surface with time expected from three-dimensional models. Also, here on the right, you see that the larval production increases at the higher and higher saturation states of aragonite. Saturation state is defined here in this green here. And here, people have calculated, show that the saturation state in a location, the Gulf of Maine, changes with a clear annual cycle that's actually quite closely tied to the seasonal temperature cycle. So there are changes going on that are changing the aragonite saturation state. So this has been considered important because the importance of calcifying organisms as a resource. Here too, we see the proportion of larvae that look normal going way up as the saturation state increases. So I mentioned that you needed two measurements, and you need all those equilibrium constants, and those all have their own uncertainties, and there are implications of doing this. If you're looking at standard relative uncertainties, that's 68% confidence, like a normal standard deviation, one standard deviation for the carbon parameters. My estimates are that for alkalinity, it's relatively straightforward to get within about 0.5%, which is about 10 micromoles per kilogram. Total carbon, again, about 0.5%, not quite so straightforward to do, but about 10. For the hydrogen ion concentration, 5% is reasonable, which is an uncertainty in the pH of about 0.02. PCO2, about 3%, it's about 12 microatmospheres. The constants have uncertainties as well. And all of these are, I feel, reasonable estimates based on interlaboratory studies over the last decade. That is, that many laboratories can achieve this straightforwardly. Some can do better, but usually those are laboratories in labs with a lot of experience, usually in first world countries with expensive equipment. And if you take all these uncertainties and look at a seawater that's got a pH of about 8.1 and aragonite saturation about 2.5, you can see if you calculate from pH and total carbon, then alkalinity you'll get within about 1%, PCO2 within about 6%, carbonate ion within 8%. You recall the GOA-ON weather said carbonate ion within about 10% was fine. The only one you don't get 10% is if you're doing it with pH and PCO2 with these uncertainties. Then it's a little bit bigger. On the other hand, if you drop the pH to a fairly acidified seawater, one last point here, sorry, you can't actually calculate anything better than you can measure it. So if you want something that you can measure, you always do better to measure it. If you go to a lower pH and saturation state around 1, then again, that one is problematic, but also here with total carbon and alkalinity, it's hard to get a well-known carbonate ion concentration. So let's just talk a little bit about what you need to make these measurements. There's a series called Valid Analytical Measurement Principles that came out in the UK basically around a little bit before 2000, I think. And they had 6 things. That you must make the measurements for a reason. Don't just make measurements. You're doing it because you need to do it. It's an agreed requirement. They're made using methods and equipment that have been tested to ensure they actually are fit for purpose. It is that they can satisfy this agreed requirement. The staff making these measurements need to be qualified and competent. You need to check that you're actually doing the work well. It's an independent assessment of the technical performance of a laboratory. The goal is that analytical measurements made in one location, that's a particular laboratory, will be consistent with those made elsewhere, other laboratories. Of course, if you think about ocean acidification, the geographic location of where the samples came from also makes this matter. And finally, that you need to have well-defined quality control and quality assurance procedures. So let's just break this up into 3 major categories. First, these 2. Both of these really mean that you need this idea of a measurement uncertainty associated with each parameter that's being observed, because then you can have an agreed requirement and you can tell whether or not you satisfy it. If you do that, if you know the uncertainty and you're within the desired uncertainty, then it doesn't really matter where the measurements were made. They're equally useful. This one note is perhaps the key part of success. The staff should be qualified and competent to undertake the task. Without this, the people involved are the most important piece. Without this, you don't get good data. And then these 3 really just emphasize the need for effective laboratory quality control. So 3 items. First, you need to know what uncertainty is appropriate for the problem you're trying to study. And therefore, you need to be able to say, and I can estimate that uncertainty with reasonably well. And the quality control shows that you're actually achieving what you wanted. And both of these really need capable, trained people to do it. So in conclusion, the simplest measurements perhaps that you can do for this, and they're incorporated in the GOA-ON in a box that the Ocean Foundation provide, is an acidometric titration of total alkalinity, which is considered relatively straightforward, in part because much chemical analytical training involves doing titrations with acids. Here's a particular technique for a particular result, but it's adding to people's prior knowledge, not replacing it or giving something completely new. And colorimetric measurement of pH, and we're using indicated dye meta-Cresol purple. There are a couple more talks about that, but the key here is, again, this is an idea that's relatively straightforward for a trained chemist to understand and to comprehend how best to do it. The equipment in the GOA-ON in a box is substantially cheaper than that used to make state-of-the-art measurements. I think on their website, it says it's about 10% of the cost. And that's probably still true, even as the costs keep going up on both for simple equipment and for more expensive. But it enables scientists to make measurements that achieve the GOA-ON weather quality, that 10%. It enables them to do it with equipment that's easy to use. However, it does require careful and skilled work by people, because much of the benefit of the expensive equipment is that it's at least partially automated, and thus replaces the need for an individual to be scrupulously careful at all times. It's not really clear how you best train technical personnel to make these measurements. There are instructional videos for the GOA-ON in a box available at this rather horrifying looking address. Using Google to help you would probably be more effective than trying to type that. But my own lab's experience about training people is, I think, salutary. We build and sell people state-of-the-art alkalinity titration systems. And I usually would say to those people that if you come in to a working system on the bench in my lab on Monday morning, I'll probably have you doing the best measurements in the world or near the best measurements in the world by lunchtime. So after a few hours of experience. But the bad news is if I walk away then, by the end of the week, you will no longer be doing the measurements that well, and you will not know that you are doing them worse. And it takes a number of extra weeks of training to say, how do you do the quality control that allows you to feel comfortable that you're maintaining that each measurement is as good as the next? But then something breaks. And it may break insidiously, so it's just not working properly. How much experience do you need to figure that out? And then finally, what do you need to know to be able to repair any problems, replace any parts, and get back on to day one, where you're making as good a measurement as you were originally? And all those pieces are needed in the training. And most training, and certainly in these instructional videos, is aimed at that day one of what I think is at least a year's work.
Mm-hmm. Thanks,
So,
Andrew. Going to have
you.
to ask you to wrap up there, but I really appreciate that.
That's the
I'll
end.
say from the Ocean Foundation's perspective, we've really greatly admired and appreciate all the work that you've done to translate this technical knowledge to the kit recipients that we've worked with and done some of that hands-on training yourself. That's been really incredible. All right, so I am going to be presenting next. Sarah was already kind enough to share my bio, so I'm going to launch right into it. So in my talk today, we're continuing on some of these themes that Andrew raised and talking more about the development of a set of practical best practices to focus on this oceanification monitoring with a particular focus on the GOA-ON in a box kit. And as you can see, this is a huge effort from a number of researchers around the globe. And I'm very appreciative of their contributions to the products over the last couple of years. So I want to just provide, a little bit more information about what the GOA-ON in a box kit is. It does provide a suite of equipment that's suitable to measure to that weather quality standard that Andrew shared more about for total alkalinity and spectrophotometric pH via sensor deployments in the field and then laboratory measurements of bottle samples back in the lab. And right now it's about 90 unique pieces of hardware, but there's also included software as well for the data analysis side. You can go online to the link that Katerina popped in the chat earlier and find that entire kit list on a spreadsheet with clickable links to all the manufacturers and the total price too. Andrew's right in that it's gone up a little bit the last couple of years, but still is quite an affordable option for initializing OA monitoring. And it's built to be replaceable and repairable with its modular design. So users can swap out and troubleshoot each part if there are any issues, which is less costly and complex than trying to figure out what's wrong with an all-in-one unit. And in fact, we also include spare parts in the standard kit, things like the specialized screwdrivers for the ICME pH sensors, but also extra fuses for the multimeters, so folks can really continue the sustainability of their monitoring over time. And a really key part of this kit is that it's complemented by the training that Andrew also mentioned. Assistance with designing observation programs via mentoring and coaching, planning out time in the field work together, doing data management and quality control, and then coaching sometimes online afterwards to help troubleshoot certain issues. But we are going to be talking about some written guides that complement these hands-on training pieces that I'm sharing more on today. And of course, there are existing resources available for kit users. This is not a comprehensive list on the screen, but a couple of examples. First, new users can benefit from manufacturer guides, like what Sunburst Sensors has put together for their products on their website. And personally, I think it's really an important hallmark for these low-cost equipment and technology companies to include guides like this, because it makes their products so much more accessible to those who are just getting their footing in the field and learning how to work with some of this complex technology. And among our community, we've also created some really great resources over the years. Those videos that Andrew mentioned are on the Ocean Foundation's YouTube channel for using the kit and captioned in 4 different languages. There's also the OA Info Exchange, which has tons of tips and tricks that are shared between experts and those who are looking to learn more. There's also online guides like what Remarco has put out for the Manual of Technical Procedures, which I think is really excellent and complemented with videos as well. And then, of course, tons of information on the SDG 14.3.1 data portal, like this FAQ webpage, and classic resources like the Guide to Best Practices. And so within many of these, there is some coverage of many aspects of using the GOA-ON in a box kit, but it's not as easy for researchers who are just coming into the field, not yet practical for them to have as a one-stop shop for starting at A, getting out to the field and going to Z, which is sharing their data. So we're looking for something with that level of comprehensiveness and completeness that can help researchers get started with their OA monitoring, even when they're maybe not someone who can become like an entire oceanification expert. It's just part of one of the fields that they're working on in their position as a generalist in some of the institutions where we have curiosities based. So our goal is really to create a resource that is tailor-made for the equipment and chemicals provided in the GOA-ON in a box kit. This idea of a cookbook began in 2019 at a couple of important GOA-ON and OAICC meetings, and a few goals to hone in on what we want or envisioned. So we think this cookbook, or the practical best practices, should be easy to follow and apply for non-specialists, include not only written instructions, but also photos that complement those, templates, spreadsheets, and videos as well. So lots of multimedia. Use readily available software, so Excel instead of MATLAB. Be available ideally in multiple languages to support global oceanification monitoring. We think it should be internally consistent and come as a package. So the front of the document, we're not referring to total alkalinity as AT and TA later in the document. It's standardized across. We're having a consistent format, so it's easy to flip through and understand the methodology. And we're looking into producing this online, so pieces are clickable. You can go to other resources that are more comprehensive and be able to understand that in complement to this more simple guide. So all those cross links there. The caveats is that it's not a replacement for other guides that have been produced for oceanification research, some of those which I shared on the previous screen, and it's not necessarily all for all oceanification researchers. Again, it's really targeted towards new users of GOA-ON in a box kits to obtain weather quality data. So as I shared, this effort has been ongoing since 2019. We had a couple of hiccups around COVID, but for the last year and some change, we've been back on track, making slow and steady progress. And at present, we have 22 documents that fall into 4 sections: general practices, sensors, discrete samples, and data management. And so I want to share an example of what one of those protocol documents looks like. This is one for spec pH. So you can see that it links back to the guide for best practices for more of the theory behind this technique, but also has links to those videos to demonstrate what it actually looks like when Dr. Chris Sabine is going through the protocol, and the captions in 4 languages for that video as well. Within the document, it goes step by step through the protocol. There's some information on quality assurance as well, so the users can understand what their data is looking like at the end. And then, of course, a spreadsheet as well, so they can input the readings at each of the wavelengths and get out a nice pH value at the end. And so now I do want to share some idea of what those 22 documents in the version right now consist of. So first off, there's that section on going out in the field and collecting water samples. This includes a field packing checklist. The first time folks go out into the field, or the first couple times, they're not forgetting a critical piece back in the lab. They have a nice little checklist to go down. There also is a sampling data sheet, so folks are able to collect metadata that's important for later data submission and putting their samples into context. And then, of course, a guide to actually doing the water sampling consistent with best practices for seawater storage. And this is a section that could be used by a lot of researchers, right? It's not necessarily specific to the GOA-ON in a box kit. But the next section is focused on some of the measurements that we, or the instruments that we use out in the field, the ICME pH sensor and the CTD diver by Van Essen. So there's a quick start guide for each of those two sensors to help new users set them up and get them out into the water and calibrate them as well. There's also an FAQ document for the ICME. So as we've heard from previous kit recipients, like what are the sticking points that they have? We've compiled all those bits and pieces into this FAQ, provide the guidance and share that on to other kit users. And of course, this is supposed to complement the original manufacturer guides, not duplicate them. And so once folks are back in the lab, we have guides on making the spec pH measurements. This includes using the spectrophotometer and of course all the dyes and the pipettes and cuvettes and everything for those measurements. We also include the powder to make the meta-Cresol dye. So there's SOP to go through the production of that so they can make it as needed and again sustain those measurements into the future, and the data sheet as well that I mentioned earlier. And it's a similar process for total alkalinity. It is a manual titration using a very modular system. So there's an extensive SOP that walks through setting it all up and making those measurements. This is a really great system that Andrew and Chris have put together. And then the data sheet template as well. So folks can take the multimeter readings and get out a nice TA value at the end. And then going back, or all the way to the end, once everyone has collected their data, there are some guides in this now for doing some QA, QC to understand the data, using the reference materials that we include in the kit, and how to correct for that when it's interspersed among their sample measurements. And then a quick guide for submitting their data to the Sustainable Development Goal 14.3.1 data portal, which is where we hope all these data will go and contribute to our understanding of oceanification globally. And this section is also pretty relevant for users who don't necessarily have a GOA-ON in a box kit, but are looking to learn more about data analysis and complements other tools that are forthcoming for QA and QC too. All right, and so lastly, I just want to share like where we're going moving forward. This has been a work in progress for the last couple of years, but we're hopeful to have a version out in the first half of 2024 online. So we're looking towards some open source publication methods where all the authors can keep it up to date if there are any changes. Users can go online and have it up on their laptop when they're working in the lab, or even print it out and make notes on it. And of course, we'd like to submit it to the Ocean Best Practices System repository as well going forward. And we're already looking forward to a version 2 that includes more technological pieces, like maybe selecting different kinds of sensors for different uses, a little bit more on the biological side, so how to sample out in the field, and then how to conduct those sorts of experiments back in the lab to understand this biological aspect of oceanification. What we're really excited about is a decision tree. So that will enable new users to take their thinking of what data do I need for the questions that I have in my local community, and help guide them through the sorts of questions they should be asking, or understand, given what resources they have, what they can do with that in their own institution. So we're really excited for that. And so lastly, again, I'm here on behalf of a large number of authors involved in this. So I'm happy to answer any questions and then pass along the feedback back to our working group. So with that, I will stop. And again, happy to take any questions in the chat later on, but I will turn it now over to our next speaker. So I am very, very glad to introduce Rieke Schäfer. Rieke is a PhD candidate at PTB, which is the German National Metrology Institute. Her work focuses on metrological aspects of seawater pH measurements, such as the uncertainty of primary measurements or impurities in the pH indicator dye, meta-Cresol purple. So over to you.
Thank you. Thank you for the introduction, and I'm very happy to present our work in progress here. So it's at the moment we are still kind of working on this, but I wanted to show what we are looking into in impurities in the indicator dye that's used for pH measurements. So because I wasn't sure how familiar people are with pH measurements here, I just wanted to say that if you do the pH measurement with the spectrophotometric method, there are a couple of so you take a sample, there's the MCP, which is the indicator dye, meta-Cresol, purple and long, and then there are absorbance measurements at different wavelengths, and from these absorbance measurements, the pH is calculated. So, and about 10 years ago, they found that in these indicator dye, there are impurities that have an effect on the pH measurement. So if there are impurities, the pH measurement is less precise or it changes more between different batches of MCP. And because this has an effect on kind of our knowledge of the pH, there is a purification procedure that's now recommended to use before using the MCP. So the indicator dye bought from the manufacturer is then purified, and then the purified dye is used. But at the moment, we don't really know how good the purification actually is. We know that it improves the pH measurements, but we don't have a quantification of how much impurities are there before the purifications, how many are there after the purification, and we don't know which kind of impurities are there exactly, and whether each purification is working in the same way. So if we have two batches of MCP, whether the purification for the first and the second batch actually resulted in equally pure MCP. So we wanted to look into quantifying this and better characterizing the MCP purity to better know whether we can actually compare different batches of MCP. So we started off with a method to quantify acid content at PTB, and then later added two different methods to identify the impurities. And we were lucky to have colleagues at two different institutes who did the measurements for us. This was Klaas Meyer at BAM and Martha Gladhill at GOA, who are helping us with the identification and the measurements in there. But first, the colorimetry we did at PTB. So this is a method to measure the acid content. And you can see here 100% is the acid content we would expect if it's just MCP. And for the unpurified MCP, we have an acid content that's very close to what we would expect. So you can assume either there are very few impurities in the MCP, or we have impurities that are actually acidic. And then we have the purified MCP, which has actually a higher acid content than we would expect if it's just MCP. And this is caused by an acid that's added in the purification, which apparently is not completely evaporated. It's called TFA for short, and we could confirm later with the NMR measurement that it's actually not completely evaporated. So in the purified MCP, there's an additional acid that we can see in the colorimetry. It doesn't matter for the pH measurement, but it does matter for colorimetry because we just measure the total acid content. And this means that we can't use colorimetry for the quantification because we would never know whether the change we see is caused by the TFA or whether it's actually a change in the purity of the MCP. So that is also why we didn't improve the method. You can see the scatter here is quite large, which is not a good sign for colorimetry, but we saw that this additional acid does not makes the method unsuitable. So we didn't improve the method itself and moved on to identifying the impurities to better be able to identify a method that we can use for the quantification. So we had our colleague at BAM looking into NMR measurements. And first of all, he confirmed that there's this TFA from the purification still in the purified MCP, at least in the batches we had available, in very low amounts, but it's still there and affecting the colorimetry. And then he also had this comparison between purified on the top and unpurified MCP and the bottom here. And you can see these peaks indicating different molecules. So there is a change between unpurified and purified ones that we can see in the NMR. Unfortunately, it's very difficult to identify the molecules that cause these peaks just from the NMR, but at least we were able to see a change. And what he also saw was that the solution changes if it's stored in the lab, just in the light, and for about 2 weeks, these peaks also change in the purified ones. So there seems to be a stability issue. That was just kind of a side note that we found. And because we saw these changes in NMR but couldn't identify them, we also made mass spectrometry measurements following the method that was also used by Regina a couple of years ago. We're still looking into the data, so there's not really an identification yet. And the first impression is that we have either very low concentration of impurities, or maybe the impurities didn't ionize, so we are not able to see them. The only thing at the moment we have is that we first have a liquid chromatography, so the MCP is split into different masses in the first instance. So we have one peak for where we know from the purification it's mostly MCP, and we can very clearly see in the mass spectrometry the mass of the MCP molecule. And then there's one peak in the liquid chromatography that is said to be the contaminant peak. And there we have a molecule that's very similar to the MCP. It's a little bit lighter, so 2 protons less, but it behaves very similarly, so it might just be a different form of MCP, but we don't really know that yet. And we're still looking into the details of our results. But if anyone has any input on that, we would be happy to hear that. And just to conclude and give an overview, so we have these 3 different methods we used. And from colorimetry, we can tell that the acid content itself is not the right metric to use for the quantification of the MCP purity. We can see in the NMR that the purification actually changes something, which we also know from the pH measurement, but we're still looking into the LCMS measurements, so the mass spectrometry results are at the moment difficult to interpret, but we're still working on that. And with this, I would like to thank all the people who've worked with me on this, especially Klaus Meyer from BAM and Martha Glätzel from GOA-ON, who provided the measurement and the interpretation, and a number of people from different institutes who provided me with MCP samples from different batches, so we could actually compare very different batches in the mass spectrometry. And this work is part of the SAFTIS project, which is working on the methodological basis of spectrophotometric pH measurements for seawater. So we're looking into different aspects of all these measurements and trying to improve the traceability, and are also developing the uncertainty calculation. And that's all for me. Thank you for listening, and I'm happy to have any questions later in the Q&A. Thanks.
Wonderful. Thank you so much for that talk. It sounds like quite the scavenger hunt you're doing there. Any questions for Rieke? Please add them to the Q&A box, and we'll return to them after our last talk. So I'm glad to introduce our last set of speakers, Dr. Regina Easley and Andrew Reed. Regina is a research chemist at, Okay. She's a research chemist at the National Institute of Standards and Technology, NIST, located in Maryland at the Chemical Sciences Division of the Materials Measurement Laboratory. Dr. Easley joined NIST in 2014 as a National Research Council postdoc. In her role as a research chemist, she co-manages the Electroanalytical Chemistry Laboratory, which is responsible for the production of pH standard reference materials. Additional research in her laboratory focuses on improving methods to measure the inorganic carbon dioxide system in seawater with an emphasis on pH measurements. In addition to her role as a research chemist, she also serves as an affiliated faculty member at Georgetown University in the Environmental Metrology and Policy, or EMET program. This unique program is a collaboration between GU, NIST, and the Environmental Protection Agency. And now Andrew Reed. Andrew recently graduated from Georgetown University, where he received a Master of Science in Environmental Metrology and Policy. He graduated from Lafayette College in 2019 with a Bachelor of Science in Chemical Engineering and a minor in Spanish. Andrew's incredibly passionate about ocean carbon chemistry and excited to utilize his undergraduate and graduate degrees to conduct environmental work. Welcome, both of you.
Thank you. I'll go ahead and share my screen. Okay, perfect. So hello, everyone. My name is Andrew Reed, and I'm here today with my mentor, Dr. Regina Easley, who, as Kaitlyn mentioned, is a research chemist at the National Institute of Standards and Technology and Georgetown University adjunct faculty. And we're here today to talk about a bottom-up approach for developing uncertainty budgets for spectrophotometric pH measurements in seawater. Oops, sorry. So this whole process really started about a year and a half ago when my capstone research partner, Jack, and I approached Regina and asked if there were any projects in the field of chemical oceanography that she thought we could look into for our capstone. And so she taught us about sort of the scientific tendencies of reporting repeatability instead of uncertainty for pH measurements, and then I guess diving deeper into the field of uncertainty, different methods, whether it be top-down or bottom-up uncertainty budgets. And Regina connected us with Kaitlyn, and so for the past year and a half, we've been working with GOA-ON and the Ocean Foundation to create an uncertainty calculator for spectrophotometric pH measurement methods in seawater that is to be paired with the GOA-ON box kits. And so here's a little bit about what specifically is in the kit from a pH perspective. And so this is a spectrophotometric pH measurement process. So we have our spectrophotometer here in the image to the right, instead of a potentiometric method with a pH probe. This uses a 1 centimeter optical cell and a meta-Cresol purple pH indicator dye. A little bit about the spectrophotometric pH method. Again, we're determining seawater pH using absorbance values from our indicator dye, our meta-Cresol purple dye. And the general process for this is that you will load your cell with your seawater, you'll put it in your spectrophotometer, the light will shine through, and you will calculate your absorbances at 2 absorbing wavelengths of 434 nanometers and 578 nanometers, as well as 1 non-absorbing wavelength at 730 nanometers. And after that, you take your cell back out, inject your pH indicator dye, and put that back in and measure your absorbances a second time. And from there, you can calculate your pH using your absorbance ratios and other parameters like salinity and temperature. And eventually, if you do a lot of samples with a lot of different pHs, you can get what we had at the end of our capstone, which is this plot on the top right with the different absorbance peaks. And so when we first started working with GOA-ON and the Ocean Foundation, we were presented with this spreadsheet. And so you can see your user inputs are coded in green, where you have your sample name, your salinity and temperature, dye volume, and then you have your absorbance values for your seawater and your indicator dye. And then using a lot of equations from Liu et al. In 2011, you can get all of these great calculated values that eventually propagate into your overall pH value, which is shown there in blue. And so we come in and we have been working on developing our uncertainty tool. So again, focusing on uncertainty and not repeatability. And we've been using a bottom-up approach to do so. And a bottom-up approach entails breaking our uncertainty down into individual sources of error that are attributed to each component or variable in our measurement equation. And so again, we're looking at the standard and expanded uncertainty for each term. that contributes to our overall pH value. And to illustrate this, we have a fishbone diagram here on the right. As you can see, our different molar absorbance ratios are E1, our E3 over E2 terms, our R term is our absorbance ratio, and then we have our log K2 E2 term. And so these different branches that you can see are the different variables that we plug into the equations that were defined in the Liu et al. Paper in 2011. So for E1, we're plugging temperature in, our E3 over E2 term, temperature and salinity. We have our different dye and non-dyed seawater absorbance values for our R ratio, and temperature and salinity for our log K2 E2 term. And so when wanting to eventually report our uncertainty, we have to start with identifying our uncertainty sources. So again, looking at each variable in our measurement equation, we determine if they are type A or type B. And then from there, we can quantify each uncertainty. We can convert to our standard deviations or standard errors. We can calculate our combined standard uncertainty. And then using our coverage factor K, we can calculate our expanded uncertainty. And from there, we're ready to report our uncertainty associated with our pH values. And so to build this uncertainty tool, we started with the NIST metrology for Microsoft Excel add-in, which is this fantastic tool that was developed by the Statistical Engineering Division at NIST. And essentially what this does is it utilizes analytical methods that are outlined in the GOM, the Guide to the Expression of Uncertainty in Measurement. And for my capstone specifically, I worked on building a pH uncertainty calculator in 3 formats. So a Microsoft Excel spreadsheet with this metrology add-in, an R script where I was hard coding what's going on behind the scenes in Excel in R, and then a Cragton spreadsheet, which is more accessible because on this last bullet point, you can see that this metrology package requires an R installation, and the Excel format is only available on PCs, which was an issue with my Mac computer. So we decided to make 3 different formats, the last of which being more accessible. I've included a QR code here, just the link to that metrology tool itself. So this is kind of going under the hood and looking at the NIST metrology spreadsheet in Excel. And I'll point your attention first to the tabs at the bottom. So this is our tab for our R ratio, our absorbance ratios. And if you see our pH equation to the right, that R term is boxed in red. But we have one of these tabs for each one of our measurement equation terms, and then a final tab for our overall pH value, where the inputs are the resulting outputs from each one of our component variables. So as you can see at the top, we have our input variables. We have our different absorbance values at our respective wavelengths with and without dye. We have our input values, our standard uncertainties, our degrees of freedom. And then you can choose the type of uncertainty evaluation you'd like. We use type A for this, but you can also toggle it to type B if you would like. Also looking at your distribution, we used a normal distribution, but you can also toggle to rectangular or triangular. And you can include your measurement equation below. And then you just click that nice button and you get an output value, in this case, our R ratio. You get your combined standard uncertainty, your lowercase UC, your effective degrees of freedom, which can be used with your confidence level to get your coverage factor. And then you multiply your coverage factor by your little UC, your combined standard uncertainty, to get your expanded uncertainty. And so to really make this accessible and to eliminate the need for R, we approached our work with GOA-ON by using a Cragton spreadsheet. And so this has a similar approach. We're getting our combined standard uncertainty from our input standard uncertainties and a measurement equation. And then we're getting our effective degrees of freedom from the Welch-Satterthwaite equation. And using our coverage factor K and our combined standard uncertainty, we can determine our expanded uncertainty. And so this is a really great tool. With this tab, you can see that we have one tab for each one of our inputs and then another one for the output. But with our Cragton spreadsheet, all of this can be housed in one tab that just goes along with the GOA-ON spreadsheet itself. So this is looking inside the tool at our Cragton spreadsheet. And if you look at the measurement equation on the right, this is our overall pH Cragton, but there is one for each of our individual components as well. You can see that our inputs are in the top part here. And these inputs are actually being pulled from the outputs from each individual factor's Cragton. And then we'll eventually get our output, which is shown in the bottom left, where you have your measurement function value, in this case, our pH value, our combined standard uncertainty, little UC, our coverage factor K, and our expanded uncertainty, capital U. And we also decided to compare our 3 different methods just to make sure that we're getting the same results across all 3. And we found that to be the case for our combined standard uncertainty, our coverage factor, and our expanded uncertainty. And so we went back to the GOA-ON spreadsheet that we received at the beginning of our work, and we added a few more columns in there. So we added accuracy columns after our salinity and temperature to give a little bit of a measurement accuracy information for how those measurements are being taken. We added repeatability after our different absorbance values with and without dye. And we added an indicator tab on the far right so that we can toggle and keep track of whether unpure or purified indicator dye is being used. Then we have our same calculated values, but this time, instead of just having pH on the end, we have our combined standard uncertainty and our capital U, our overall uncertainty. So here you can see that this is the very top of our Cragton tab. So as I mentioned, one tab of the Excel spreadsheet will be this here, where you're inputting your data that you're taking. And then the next tab will actually house the Cragton itself. And here, that highlighted row number, you can select which row number you're interested in. It'll automatically populate your values from the previous tab, and it'll combine them and present your output values here. And one thing that we're still working on is getting our dye purity uncertainty accounted for. And like was mentioned in the previous presentation, the dye itself has an effect on pH, so we want to make sure that those uncertainties are being properly accounted for in this tool as well. One of our biggest assumptions with this tool is that we do not have uncertainties associated with a lot of constants as they pertain to our molar absorbance ratios. So our E1, E2, E3 terms, these were empirically determined values that were used in the equations by Liu et al. In 2011, which is what we've been using throughout this whole process. And our next steps, like I've mentioned, we would really like to finish developing our dye perturbation factor to make sure that that is effectively being utilized in our tool. And with a lot of that will come some spreadsheet formatting. And we also want to highlight how applicable this tool is to other seawater parameters and really anything with a measurement equation like total alkalinity. And that's all I have. I'd like to thank you all for your time, and we're happy to answer any questions and would love to hear any feedback about if you think this tool would be very helpful or anything that you might want to see added.
Thank you so much, Andrew. That was wonderful. It's been a pleasure to see the advancements your team has been working on with this. And I think it's a really neat extension as kit recipients become more comfortable with the measurements. They're able to advance up their outputting data to meet some of the expectations for publication, these uncertainty calculations that would be useful for other researchers to know. So it's been fantastic. So with that wraps up our presentations for today. We've answered a couple of questions in the chat, but please feel free to continue adding those in. I just have one or two of my own questions. For those of you who've been working, okay, question came in from Maribel, so I'll turn it over to that. She asks, Andrew Reed, will the uncertainty calculator be available for the wider community or only for the GOA-ON in a box kit recipients?
I can answer that pretty quickly. We'll actually make it available to the wider community and in the 3 different formats.
Perfect, thank you. I think it was really clever to have those different levels of accessibility in the different formats too. Anything to add, Andrew? Perfect. All right. One more question in the chat to Professor Dickson. In regards to saturation state, why is it KSP of calcite not involved?
The KSP, of course, is involved when you calculate a saturation state. However, at this time, there really is only one set of data for KSP, and it probably has a reasonably sized uncertainty, at least 5%. And that's why the GOA-ON original definition defined it in terms of carbonate ion concentration, which basically allowed things to be compared even as the value of KSP got refined.
Thanks for that, Andrew. I have just one more question. For those of you who've been working on spec pH, and it's been neat to hear about all the advancements, are there other aspects of measuring this parameter that you think we need to improve going in the future, or extensions of your work that you would recommend us as a community continue working on to advance, our understanding of making great spec pH measurements?
My comment would just be to follow up on some of the work of Rieke, which is that the dealing with impurities effectively is still, I think, problematic. I was interested to hear her comment that impurities grow in solutions that are stored in particularly perhaps inappropriate ways, in light, she mentioned. And I think that just the general concern about dealing with about the stability of the dyes is not absolutely perfectly defined at this time. In my own lab, we find it difficult to comfortably separate the stability of the spectrophotometric measuring system from the stability of the dye as we try to do it more and more precisely.
Thanks for that. Anything else our speakers would like to add?
Yeah, I also think that just looking into the impurities more and understanding what's actually in there and how much, whether the purification is always working in the same way, or sometimes maybe the purification is not actually purifying something, because we don't know, like we have no idea whether it's removing everything each time, and that would improve the comparability between different batches.
Thanks for that addition. All right, seeing no more Q&A, I will go ahead and turn it back over to our wonderful OA Week organizers and thank all of our speakers for their wonderful presentations.
Thank you so much, Kaitlyn, and I'll echo that thanks to all of our speakers. This was a really great discussion, and we really appreciate your perspectives and participation in OA Week to really make this such a great session. So thanks again. I'd also like to thank our audience. Thank you for participating in OA Week and for all of your wonderful questions today. Please do not forget to consult the GOA-ON website. We have the entire OA Week schedule. I know we are getting towards the end of the week, but I believe we still have 5 great sessions left, 1 today and 4 more tomorrow that you are welcome to register, and we'd love to see you there. If you would like to stay up to date with the GOA-ON community, again, please consider to sign up as a GOA-ON member at our website. And finally, if you would like to learn more about ocean acidification research for sustainability, which is the GOA-ON UN Ocean Decade endorsed program, please scan this QR code and check out our website to learn more. Thank you again, and see you next time.